So I'll start this topic. The topic is back propagation algorithm. So you have studied this perceptron structure of neural network. So as you know, we can apply number of inputs to this neural network. Here inputs are shown as x1, x2, x3, xn. So number of inputs can be applied here. These inputs are connected to adder circuit. So this each input is multiplied by some weight. Here weights are shown as W1, W2, W3 up to Wn. So each input is multiplied by its weight and then it is given to adder. This adder will add all this input multiplied by weight. So here we have shown this symbol sum of xi into wi. So we are multiplying inputs by its weight. Plus here bias is also added to adjust the output. Sometimes we need to adjust output. It may be negative, we want positive. So for that we are applying this bias signal. So bias signal can also be multiplied by weight. It depends upon application or the structure of perceptron or neural network. So here actually WB is not written, but this sum is added with this bias multiplied by WB. So this is the output of adder of this perceptron. So this output should pass through activation function. So as you have studied activation function, number of activation functions are available, like the step activation function, sigmoid activation function that we have covered in class. So this output of adder should pass through activation function and then actual output will get here as a Y. So this is the perceptron. So using this perceptron, the neural network is constructed. This is one node of this neural network, and number of perceptrons, if we connect together, then it is a neural network, or we can increase the number of layers also to get the multi-layer neural network. So you have studied already this, and using this single perceptron, we can classify this so using perceptron, we can classify linear classifier, or we can generate a linear classifier, as we have discussed for the solving a problem of AND gate and OR gate, where the output can be classified linearly. So that is possible using single perceptron. But as we have seen in XOR gate problem, the output is not linear. So you cannot classify. So we cannot classify this output of XOR gate using linear classifier. So to classify a non-linear output like a XOR gate, we need a multi-layer neural network. So XOR problem, I think that you have seen that video of solving XOR problem and you have solved it. So we'll continue a next topic. That is multi-layer neural network. This also we have discussed in class. It is having number of inputs here, and these inputs are connected to number of layers. So these layers are called a hidden layers. So this number of hidden layers depends upon the application, for which application you are designing this neural network. So according to that, designer decides the number of hidden layers. And then the output layer. Again, the number of nodes in output layer depends upon application. Here only 2 nodes are shown, but here also we can add a number of nodes. So this is the simple multi-layer neural network. Each node is one perceptron. So this is one perceptron, this is one perceptron. So like that, we are combining perceptron together, and then we are constructing this multi-layer neural network. Lot of applications are there of this multi-layer neural network that also you have to study. We can use it for classification. We can use it to extract important feature from images or from any given data. So a lot of applications are there. One of the application I am showing here. So you may be thinking why these outputs are more than one, why there is not only one single output. So in this example, there are 10 outputs are shown. So these are the output nodes, 1, 2, 3, 4, 10 output nodes are shown, and this is the neural network. The hidden layers of neural network are not shown here. These are the inputs of neural network. The hidden layers are there. We don't know how many hidden layers are there, but here output node is shown here. So what we can do after training this multi-layer neural network, that means all weights are assigned properly and network is trained. Now we want to test whether this network is working properly or not, or we want to find answer of any image. So this input image we are applying to this neural network just to check whether it is giving us proper answer or not. So as you can observe, this is a digit 1. So we are providing here the input image with digit 1 that is applied here. And what output we have got at this Y0 output or first output, the data is 99%. That means this input image matches to this output. Output is digit 1 as a 99% and digit 2 61%. Digit 3 33%. Digit 10 again 65%. So as you can say that these are the probability. So it matches to digit 1 to 99%. So we can say that the input image is of digit 1. So for this type of application, like probability we want to find or percentage we want to find, the number of outputs can be more than one. So this is just one application. Other applications you have to study afterwards. So this is the multi-layer neural network. Now we want to check how to train this multi-layer neural network. So this is the example of multi-layer neural network. Here we are considering two inputs, X1 and X2 are the inputs, and these branches from X1 are connected to hidden layer. Here there is only one hidden layer, and this hidden layer is having two nodes, H1 and H2. So there is only one hidden layer. So X1 is connected to H1 through this weight W1. X1 is connected to H2 through weight W2. Similarly, X2 is connected to H1 through weight W2 and X2 is connected to X4 through weight W4. This X1 is connected to H2 through this W3. Similarly, weights are assigned to these branches also. Here the hidden layer nodes are connected to output node. So O1 and O2 are output nodes. Now the bias are given as a B1 here. So for both these hidden nodes, the same bias is used B1, and for these two nodes, same bias is used as a B2. Now while training this multi-layer network, we have to training means what? We have to find values of this weight. For particular application, after designing neural network, the aim is to find the value of W1. You have solved the problem of AND gate, OR gate, and XOR gate using neural network, but in that case, we have directly assigned values to this weight. Directly, I have given you values for each weight and you have computed the output. That is called as a feed forward network. Directly values are given, just you have to solve the problem and you have to check the output of that particular neural network. But the thing is that how will know the values of this weights for particular problem? So for that, you have to train a neural network. That means you have to find values of this weight for particular application. So number of ways are there, number of methods are there to find or to train this multi-layer neural network. So here you have to study one method, that is back propagation of algorithm. So what is main concept of back propagation algorithm? Initially, randomly you have to assign the values to all these weights. So any value you can assign to this weight, random values will be assigned, and then as a feed forward network will compute output. In this case, two outputs are there. So you have to compute these outputs O1 and O2. That is like a feed forward network that already you have solved. After that, you must know for the particular input what should be the output. That we called as a target output. Actually, we want to design this network so that for particular input, we want a target output, some output we want. So we are designing a network for that particular output. So for that particular output, we want to find the values of this weight. So we'll randomly assign values to this weight. We'll compute this output, and this output we call as an actual output. Then we calculate the error between target output and actual output. And then using this error, we'll start updating this weight in backward direction. Again, we'll compute the outputs using feed forward network and calculate the error. So we have to repeat this process. We are going to check all these steps. So we have to repeat this process till error becomes 0 or very small. So now we'll start a back propagation algorithm. So you are going to study back propagation algorithm using this example. I have scanned these diagrams for this calculation. Lot of calculations are there. So actually it is better to teach on blackboard. But now I have written it on the paper and scanned this diagram. So this network, using this network, now you are going to study how back propagation algorithm works. So the network is simple. This input is x1. The second input is x2. The input values are given 0.05 as x1 and 0.10 is x2. What we want to do, we want to design this network such that for this set of inputs 0.05, 0.10, we want this output 0.01. We call it as a target output 1, and this is target output 2. So that is 0.99. For this input x1 0.05, we want PO1 0.0001 and when x2 is 0.10, we want this output. So this we call as a target output. Now we have used here again one hidden layer with two nodes. So this is the output of this hidden layer node h1. I call it as a h1 dash. This has to go through activation function. This is the output of h2 node, h2 dash. This has to go through activation function. Then output after activation function at this node is denoted as h1. Output after activation function is h2. This is h2. And then this h1 and h2 are multiplied by corresponding weights, and they are applied to next step, next output layer nodes, that is O1. This is output layer node O1. This is output layer node O2. Now this output again has to go through activation function, and then we'll get a target output 1. This output O2 again has to go through activation function, and then we'll get a target output PO2. Here we have used a bias. B1 dash is the bias, that is 0.35. B1, B2 dash, this is B2 dash, you can, are not able to see this. The value of this is 0.35 and these values are random values. Initially, the random values are assigned to weight. You can assign value 0 also. So random values are assigned to this weight. To solve this problem, I have selected this values. I'll share the PPTs with you and this recording also, so you can solve this problem. This is the B1 dash, which is used for the upper node of hidden layer, and B1 and B2. So this is the neural network. Only remember that these are values of input x1 and x2. For these inputs, we want these output. This is our aim. For this set of input, we want this output T01 and T02. For this, we are designing this neural network. And for that, these weights are randomly assigned. So this B1 dash, all these values are random values. So this is our network. Now we'll train this network so that for this particular input, we'll get this particular output. So we'll start training of this neural network. Same diagram I'm showing here so that you can understand this. The activation function we are going to use is sigmoid activation function, and it is this is the expression for sigmoid activation function. We have discussed this in class. The nature also you are having in your notes. That is 1 divided by 1 plus e to the power minus f. In XOR gate problem, we have used state function as a activation function. But for this problem, we are going to use the sigmoid function. This is why, because in state problem, you will get a output as either 0 or 1. So that we have used for gates problem, AND gate, OR gate, and XOR gate. But here we want the output other than 0 and 1. That means values we want 0.01 and 0.99. So we have used here sigmoid function. So depends upon application, the functions can be selected. So we'll start solving this. We'll start solving this problem. So first we'll find this H1 dash. As you know the process of finding this H1 dash, we have to multiply X1 by W1 plus multiply X2 by W2 plus add this B1 dash. Here weight for B1 dash is not used. Generally weights are not used for B1 dash, but again it depends upon an application. So this is solved here. You have to solve it afterward in your notebook. H1 dash is x1 into W1 plus x2 into W2 plus B1 dash. That is the bias component. So substitute here values, and for bias also you will get this value of H1 dash. So this is this H1 dash, that is actually the output of this hidden layer before passing through activation function. So this is H1 dash. Now H1 is output after passing through this activation function. So now H1 dash will pass through activation function, that is transfer function, and then we'll get the actual output of this hidden node, that is H1. So since we are using sigmoid function, here H1 formula is 1 divided by 1 plus e to the power minus H1 dash. H1 dash is input function to this activation function. So simply substitute the value of H1 dash here. You will get the value of output at hidden node H1. So I think that you have understood this. It is very easy, and you have used this formula for XOR gate calculation, that is feed forward network, and we are solving feed forward network only up till now. Then same method, using same method, you have to find this H2 dash. So H2 dash is equal to X1 into W3 plus X2 into W4 plus this bias, that is B2 dash is 0.35. 35. So this formula is written for sum and substitute the values, you will get this output. Now again h2 dash is passed through the transfer function. We want the output h2. So we'll pass through this transfer function. h2 dash value you have to substitute here. You'll get this value. So try to solve it afterwards. So till now what we have computed h1 and h2. These two values we have got. This h1 and h2 are actually input to this output node O1 and O2. So in the similar way, we can find O1 and O2 and output of this node will find. So go to next step. So first we will find O1. We know H1. So O1 is H1 into W5. So W5 into H1. W6 into H2. So W6 into H2 plus here bias is used, that is B1. So this is B1. So this O1 output we can compute using this sum formula. Simple sum formula. We are multiplying input by weight and we are adding it. And bias component also we have to add. So we got this value as O1. So this is the output to this node before activation function. Here also we are using same activation function. It is not necessary that the activation function at each layer is same. You can use different activation function also. But this is a simple problem. We'll use the same activation function, that is sigmoid function. So 1 divided by 1 plus e to the power input. Input is 1.156. So you will get this value as a AO1. So I'll call it as a AO1, that is actual output. So here you will get AO1. So here we are getting actual output, that is AO1. So this is actual. Remember the difference between TO1 and AON. This we want. This is our target. But what output we are getting? 0.7601. So output is more. With this random values of weight, output at AO1 or first output is more than the actual output. What we want? 0.01. So to get a 0.01, you have to change now values of weight. So AO1 we got is 0.7601. Similarly, we'll find AO2, that is actual output for output node 2. So the same diagram, here we'll find O2. So O2 same way, W7 into this H1 plus W8 into H2 plus this bias B2 0.60, same bias I have used here. Then solve this with this values, you will get this value 1.254. So again this O2 should be passed through activation function. So AO2 1 divided by 1 plus e to the power minus 1.254. So here you get a value of AO2. It is actual output we are getting with these values, and this is a target output, that is 0.99. So in this case the actual output with this random weight is less than the target output AO2. Now we have to update this weights. We want to change this weight so that we get this target output. So that is called the training of neural network, and for that back propagation is used. Back propagation means we'll go back in backward direction to update the weights. That means first we'll update the weights of this layer, and then we'll update the weights of this layer. So since we are going in backward direction to update the weights, it is called the back propagation algorithm. Number of methods are there to update these weights or train a neural network. So now what we have to do? We have computed here AO1 actual output. Here also we have computed AO2. Now we want to find this error, how much error we are getting. So this is the formula to find the error, half of that is square error. So target output in this case TO1 and TO2 minus actual output and square of this, and we are using this formula, half of this. This is formula to find the error at this each output AO1 and AO2. So we'll find this error. Using this error, we are going in the backward direction. So this is the formula for error calculation, that is square error formula. You have studied it already. So this error we will calculate first as a total error. Since we are having two outputs, the errors will be calculated considering both the outputs. So this is the formula to find the error at the output node. That is sum of half of target output minus actual output square. So sum, two outputs are there. So we'll find first the error because of first output TO1 minus actual output AO1 square half. This is formula to find error for the second output TO2 minus AO2 square. We'll add this. So we'll get a total error at output layer. That is half 0.01. We have already computed these values. We'll just substitute here and we'll get this error 0.2813, 0.0224, and then the final total error is 0.3037. So we have computed error. Actually, we want target output, but we are getting actual output. So what is the error that we have computed? And this is the value of this total error. Now the thing is what to do with this error. Now if you plot this error with a weight on x direction, error in y direction. This is called the gradient descent. So in that detail we are not going here. Just to understand this, we want a zero error. So we want to reach this point. Error between our actual output and target output should be minimum or it should be zero. So generally this type of graph is used in gradient descent algorithms. So suppose you are here, your error is with this value. Then what you have to do? We have to increase the weight to reach this point. So if you are on the left side of this line, so you have to increase the weight, go on increasing the weight so that you will get an error as zero. If you are on the right hand side of this line and suppose you are here, so what you have to do? You have to reduce the weight to get an error zero or less error. So this is the other point, the important topic, but we will not go in detail of this. So, but you can understand from this graph. So you have to increase the weight, or you have to decrease the weight accordingly, depends upon the error and weight. Now here I have drawn a one node, output node. Just take this node. So I have drawn it again. This is the output O1. This is the activation function. This is the actual output 1. And here we are getting a total error. We are considering total error, not only one particular error. This is the bias. This is the input. One input is shown here. Here it is W6 and all that. Now what we are going to do, we are going in a backward direction. So first in a backward direction, we'll start updating or we'll start finding a new values of this weight. We'll take an example to find a new value for W5 as according to error. We have to update this weight. So we have computed error at the feed. It is like a feedback. So this error we are using as a feedback. So here at this end, we are having this error, and here we want to update this way. So for that, first you have to compute partial derivative of E total versus W5 with respect to W5. So what we are finding actually, we are finding what is the effect of W5 weight on this total error. So what is the effect of W5 on this total error? For that, we are finding this partial derivative. Actually, it is a gradient that is related to slope of this line and all. But here, just remember that we are finding the effect of W5 on total error, so that we can, what is the contribution of W5 on this total error that we want to find. So for that, we are finding the partial derivative of total error with respect to W5. So directly it is difficult to find the partial derivative of E total with respect to W5. So from this diagram, we can write this formula to find this partial derivative. What we'll do, first we'll find the partial derivative of E total with respect to AO1, because directly E total is connected to AO1. So we'll calculate this step by step. We'll find the derivative of E total with EO1. We'll multiply it by derivative of AO1 with respect to O1, and then we'll compute the derivative of O1 with respect to W5. So what will happen if you cut this? Actually, what we are getting this partial derivative of E total with weight W5, and that is our aim. Why we are finding this? We want to find the contribution of W5 on the error. For each and every weight, you have to do all this process, and that's why the software are used to develop a neural network. It is very difficult to do it manually. But just to understand this algorithm, I'm explaining this problem. So we want to find this, and use directly we won't find it. It is difficult. So we'll divide it into this three factor. Hope that you have understood this, how we have written this. So E total is directly connected to AO1. So we'll find the partial derivative. AO1 is connected to O1. We'll find this partial derivative, and then we'll find this partial derivative, so that we'll get this value. So we'll start computation. Now how to find this partial derivative? Now we know that the formula for error, that we are using the square error formula, this formula we have used to find this E total. So we'll take a partial derivative of E total with AON. The simple derivative, you can find it with respect to AO1. So this is 0, this will be 0, and the derivative of minus AO1 is minus 1. You can do it afterward also, and this 2 will be multiplied here, and you'll get this value. So because of this minus sign, you'll get this partial derivative value as minus TON minus AON. We have already computed TO1, AO1. So we'll substitute here, and we get this value, 0.7501. So this is the value of partial derivative of this error with respect to AON. So first factor we have computed. This is our formula. This we have computed from this formula. The next is compute this value. So this value now we want to compute. Now AON, that is the activation function. Input is passed through activation function, and then we are getting this particular AON expression. So this is the expression for AON. Input for this is O1 as it is written here. So we have to find partial derivative of this with respect to O1. So that mathematical part you can find, you can compute afterward. But if you differentiate it with respect to O1, we'll get this particular formula. That is AON multiplied by 1 minus AON. You can do it as a homework. It is easy. The direct formulas are also given, but this is the final answer of this partial differential or derivation. So if you substitute this value, you will get this partial derivative as 0.18234 for our particular net. The next factor is partial derivative of O1 with respect to W5. So we know the formula for O1. Now you are expert in writing this formula. Multiply input by weight. All add all this and then add this B1. That is the bias input. We'll find the derivative of this with W5. We want this derivation with W5. So you will get the answer as X1. And this is the X1. So hope that you have understood this. Not very difficult. I have simplified it. So try to solve it. Now our aim is to find the contribution of W5 on this total error. So for that we have used this formula. We have computed all these values. So substitute these values here. You will get this answer. Try to solve it. So this is the contribution. This is the value of this partial derivative. For W5, we have computed only for W5. For each and every weight, you have to perform this calculation. So we got this, the effect of W5 on E total. Now here comes the delta rule. I have given one question on assignment also. What is the delta rule? Explain the delta rule. Using delta rule, this back propagation algorithm is developed. So delta rule is used to find the new value of weight. After finding the error, you have to compute a new value of each weight or update the value of each weight. So for that, this formula is used. For any weight I, so Wi new value is computed as old value of Wi, random value which we have assigned, minus alpha into this contribution of particular weight, in this area. Now here alpha is learning rate. How fast you want to train your network. That is alpha. Or how slow you want to train your network. Always slow and steady network is better. So value of alpha is selected in the 0.5, 0.6 like that. So we want to train our network slowly so that we'll get a steady and proper response. So alpha is learning rate. It depends choice of designer or depends upon application. You can select the value of alpha. So this is the formula. In our case, here we are finding a updated value for weight 5. So W5 new, that is equal to W5 minus learning rate. How much fast or slow you want to train your network, because you have to update these weights continuously till you get a very small error or zero error. Again, it depends upon the designer. He can decide the error value. So this continuously you have to update till you get a targeted output. That is called the training of neural network. So for in our example, we are studying for updation of weight W5. So we'll use this formula. So W5 new value will be computed as W5 minus, here I have considered learning rate as alpha. We are not developing this for any particular application. So just randomly we have selected alpha. Again, there are a lot of methods to select the alpha, how to select alpha and all. But here, to keep it simple, we'll use a small value of alpha as 0.6. This is our partial derivative. So we'll solve this. You'll get new value of weight as 0.4313. Take a previous value. Now this is the new updated value. This is for W5. For each and every weight, you have to go through this steps and you have to find its new value. After computing these new values, so first we'll find the updated values for all these weights, and then again we have to go back using the same process. You have to find the updated weights for W1, W2, W3, W4 in this example. After finding the new values of all these weights, again compute the output using feed-forward neural network. Update the weights, again find the actual output, find the error, update the weights till error becomes 0 or very small. So this is the back propagation network or algorithm where you are going to update your values of weights in backward direction. That's why it is called a back propagation algorithm. So the symbol way we can understand this back propagation algorithm using this step. First step is choose the weights of the network randomly. Random values you can assign value 0 also. Then feed forward computation. As using this formula, we are computing actual output for each output node. Back propagate to the output layer. That means first update the weights of output layer. Then update the weights of hidden layer. After updating all the weights, update the weights, all weights, and then algorithm is stopped when the value of error function has become sufficiently small. So when error is 0 or very small error, you can stop this algorithm. So an exam question will be asked, explain back propagation algorithm. So you can write a short note on back propagation algorithm. Along with that, you can write this algorithm. So here, initialize each Wi to some small random value until the termination condition is met, that may be with error 0 or very small error. Do what you have to do for each training sample. I have shown you only one training sample. That means only one value of x1 and one value of x2. We have trained this particular multi-layer neural network. But in practical way, in real-time application, the sets of inputs are also more. For each and every input set, you have to train this neural network. So for that, in algorithm, it is written for this number of inputs for time period t, sets of inputs. What you have to do, input the instant to the network and compute the network output. Here it is written as OK. For each output unit k, find del k. That we are doing. Find this partial derivative, that is contribution of each weight to the output error, total error. Do for each hidden unit h. Again we have to find using this formula for hidden layer, del h. For each network weight Wi, what you have to do? You have to update the weight using this formula. The new weight is equal to old weight minus alpha. This is the learning rate into this Wk or Wh. This is or not divided. You can use the Wk if it is the output layer. You can use here not Wk, del k or delta k if it is a hidden layer. So this is OR, not divided by. Alpha is a training rate. So this you have to do continuously till error becomes 0.